Okay, so we've got these definitions. And we understand what is going on, like why an object-oriented language was created, what the central principles are, what the central tenets are. But what are the principles of object-oriented programming? So we have three central principles of object-oriented design and languages. Encapsulation, the idea of inheritance or abstraction, and polymorphism. Okay. Polymorphism leads to modularity, inheritance leads to abstraction. Encapsulation, let's start there. What is encapsulation? Well, if you think about the word, right, it's something encapsulated, something surrounds something else. Encapsulation is that process of hiding information and more importantly, capturing all aspects of information inside of an object that is necessary for that object to work. Right? So information hiding is part of it. My player, my PC object will have all of the information that I need for my player character to function. The list object, the list class, defines all of the information that the list needs in order to work. Nothing more, nothing less. And then it hides that information from other objects so that objects have to interact with it through the defined message passing, the defined interface, the behaviors provided. Okay. If you take all that information that you need for an object to work, for a class to be defined, and you define it inside of the object, then that object, that class, that program stands on its own, right? And it contains everything that it needs to run. So that's the idea of encapsulation. Now we have the idea of inheritance and abstraction. And these are separate but highly related concepts, where inheritance is the idea that you're going to reuse code based off of another section of code, another object, right? An existing class. And we're going to use different terms, right? If I say a program is a subclass of another program, the derived class is the subclass, and the class derived from is the superclass. Subclass automatically inherits all state and behavior from the superclass. Okay. You might also hear me use the word extend, right? A subclass extends a superclass. What does this mean? Well, subclasses automatically get state and behavior, but state and behavior can be added in the subclass. It can also be changed in the subclass, right? What this means is that the subclass has more robust functionality than the superclass. And in many cases, you can think of subclasses as being more specific instances of superclasses, right? So a subclass extends the behavior of a superclass. And as you can even see here, we get an object hierarchy. An athlete, the concept of an athlete, right? versus the concept of a football player. Versus the concept of a skill position. Versus the concept of a wide receiver. Right? A football player is an athlete. A wide receiver is a football player. A skill position is an athlete. But each of these levels, you get more specific. A football player extends athlete. Skill position extends football player. Behavior becomes more specific. Okay. And you can have different things, right? Football player versus a soccer player. Versus a baseball player. All right. My favorite story of John Kruk, former Phillies first baseman, was he was at spring training, and after spring training, he was at a bar. He was drinking a beer and smoking a cigarette, and a woman came up to him and said, "Show some respect for yourself. You're an athlete." And he responded, "Hey, lady, I'm not an athlete. I'm a ball player." So maybe baseball player doesn't belong here. But, okay, so what does this have to do with abstraction? Well, none of these classes, none of these objects are wide receivers or actual baseball players or actual football players or actual athletes. Right? Our player character isn't an actual player or character. Right? A peanut is neither a pea nor a nut. No, wait, it is a nut. But in these cases, they're not. These are abstractions. Abstractions are the idea of capturing only what is necessary to describe a concept. So, when we're describing an athlete, we need to describe only what is necessary. We need to capture only what is necessary to describe an athlete. We don't want to capture too much. We also don't want to capture too little. Right, we have a visualization here. Oh, this is on the same page, so I'm going to get rid of this. There we go. If we capture too much, it's too realistic in this case, right? This is a visualization. We have too much detail. That is going to result in code that is hard to maintain, where a lot of the aspects of the code are unnecessary. Too abstract, and you get code that doesn't capture details that you need. Right? However, by then putting these things in a hierarchy, if we continually get what's just right, we're going to add details as they are needed. Height and weight might not be necessary for a baseball player, but is definitely necessary for a football player. Right? How fast you can throw is necessary for some football players, all baseball players. Almost certainly not necessary for soccer. Definitely not necessary for hockey. So putting height and weight and arm strength at the athlete level is definitely not necessary. Putting arm strength at the baseball player level is necessary, but might not be necessary at the football player level. It's definitely not necessary at the soccer player level. Maybe you put arm strength on a goalie. You definitely put arm strength on a quarterback. Right? By constantly refining your abstraction with the level of specificity of an object in the hierarchy, you are going to find that your code not only becomes easier to maintain, it's going to make more sense, right? Too realistic, you get a bloody mess. Not realistic enough, you get Super Meat Boy over here. Okay. This is how abstraction and inheritance is related. Finally, we have the ideas of polymorphism and modularity. Okay, so polymorphism. For the polyglots, poly, that's a clue. For the polyglots in the room, what does this mean? Oh, we got the Greek, right? Poly for many, morph, form or shape, many forms. Polyglot, right? Many tongues. Glottal, your mouth. Polymorphism is the concept that the exact same action can be handled differently by different objects. Okay. This is super related to the idea of subclasses, of how subclasses override behavior, and of duck typing. Right. The interpreter goes a.append. Okay, what kind of object is A? Because the kind of object is going to determine what sort of action append takes. Right. So let's say we have that. Let's say that we have that hierarchy that we had. And I'm not going to rewrite it all out, but I'll go ath, and I'll go base, and I'll go sock, and I'll go foot, right? So here's our hierarchy. And in football, we have skill or line. And here we have QB or wide receiver. And here we'll go mid or goalie. Right? Okay. So here is our hierarchy. And we've got a wide receiver object, and we call .getWeight. Well, I want to get WR1's weight. Get weight, not gut weight. Where does the interpreter look for this stuff? Where does it look for the information on get weight? Does it look here? Does it look here? How does it behave? Well, what it wants to do is it wants to find the most specific version of get weight. Because we might have redefined this method 2 or 3 times. So what it does is it starts looking at wide receiver. And it says, hey, do you have a get weight method? You don't? Okay, well, let's go back up. Let's go back up our inheritance hierarchy. What about skill player? Do you have a get weight method? You don't. Okay, well, let's go back up. Let's go to football player. Do you have a get weight method? Oh, you do? Okay, let's use that. Okay. Speed, get speed. All of these players need a speed. So it might go all the way back up to athlete. Or speed might be redefined at skill player. So we won't get all the way back up to athlete. We'll only get the skill player speed. Interpreter will handle a method call within the specific class, and if that definition cannot be found there, it will continue to search up the immediate supertype all the way to the root of the subtree. Okay. Once we get to the root of the subtree, it goes all the way up to the base object in Python. All things are objects. and they have some basic methods. And you'll see some of them. We'll talk about some of them. If in that entire path from the specific class that we started off at all the way up to the Python object, if we get all the way to the top and we still cannot find that definition, that's when our interpreter burps. And it will say, I can't find this. This is not defined. This attaches itself to the concept of modularity because it's allowing you to write code that is separate, right? Okay, I don't have to worry about what the get speed or the get weight or the move or the damage methods do. I can let that object handle it specifically, and it'll know very specifically how to handle it. And I can allow more specific versions to handle it more specifically. Okay. The flexibility of being able to define objects with behaviors, but not have the object be specifically bound to those behaviors until the object is run is one of the major aspects that allows object-oriented programming to be as flexible as it is. So, benefits. What are the benefits? We have a clear modular structure, and clear structure provides context to the data. Right? We're going to have flexibility because these objects can be placed wherever. Aspects of the objects are flexible, and information inside of the objects have context. So you know not just what they're supposed to mean, but what they actually mean. And the nice thing is, because information is encapsulated, classes can be reused in other applications. Right? If my player character class contains all the information for a generic player character, and I realize, oh crap, I'm making another video game, that's going to be useful. I can just pull that in and it's go time. Extending an object to new functionality is also very quick, very direct. You only change the things that you want to change. You only add the things you want to change. Everything else stays as it is. And you don't even have to redefine it. It's automatically there. Right? The football player is an athlete. That's the term, is an athlete, right? That's how we talk about it. It is a subclass. It extends athlete. It is an athlete, which means everything defined in athlete is automatically in football player. So you can look at it and go, okay, I know that whatever the interface for athlete is here, except for these changes. And cannibalizing an object, that's not an actual term. That's just a description by me, is actually very quick and direct too. So if you look at it and you go, oh, okay, I've got this PC, but I don't need that status stuff. It's easy to take an object that is like 95% of the way where you need it and just take that code and alter it. Okay. Number of times I've done that, I can't count. And there is a vast library of design patterns already in existence. You can take, I've taken a graduate level class in software engineering all about object-oriented programming, not even architecture, object-oriented programming design patterns. So there's a lot of information out there already. So you don't have to reinvent the wheel every time. So what are the drawbacks? And here's where Professor Rumbaugh gets very excited because he is a C programmer. And every time I talk about object-oriented programming, his eyes roll back in his head. So what are the drawbacks? Well, the big one is that behavior is tied to object state. So if you have something that is a truly object-oriented programming language, you have to associate that function any function that doesn't rely on internal object structure, you have to, by rule, associate it with an object. By the way, those of you who have coded in Java or C#, that is what a static method is. A static method is a function. Right? Static methods have no access to instance variables, only static variables. And generally speaking, you pass in all the information that you need, and it poops out the information that you need to get out. That's a function. But unfortunately, you have to tie that to some object. And sometimes it makes sense. If you have a static method or a function that takes some random type as an input and spits it out as the type of object that you're working in, right? It takes a floating point value and spits it out as a string, because string dot parse. Well, that makes sense. That absolutely makes sense. But then there are other times where you have to associate with an object that makes no sense because it has to in a purely object-oriented language. Strict adherence to object-oriented programming can lead to bloated code or single-use functions, single-use methods. See, even there, sometimes I slip up. Keep me on this. My last gig before coming to work at Harrisburg University, I was only there for like a month and a half, and I worked for the company that does the Easy Pass software, like you see on the Turnpike and other places. And they use a true strict object-oriented pattern and design paradigm. And when I would alter functionality, like, okay, you click this button and it calculates your fee. Okay. So I would think that you would go into the button event and see where the calculation was. Well, what I frequently found was I would move into that button event and it would literally be a single line of code that would call a function. And then I'd go into that line of code, I'd go into that function, and it would be another line of code that would call another function or method. And then it would go into that line of code and it would be another method with a single line of code that called another method. And this could go 4, 5, 6 calls deep. And the worst part is that these methods were only ever called in that one place. So you had 3, 4, 5, 6 method calls back to back to back to back, all of which are only ever called in those specific places. So you can get some nasty overhead for simple objects. Python is at least nice in that Python code's fairly compact, right? A long file, and not a ridiculous file, but a reasonably long file in Python is 100 lines of code, maybe 200. I will tell you that just creating an object in Java that does nothing, literally defining the object most basically possible, using good programming practices is about 20 lines of code. There's no way around it. An object that does literally nothing but can be constructed, you're looking at 20 lines of code. And because of this enforced structure and the fact that you have something that is controlling state for you, remember, object-oriented programs are controlling state. They are preventing you from doing what you want. Those structures take overhead. So object-oriented programming can be slower due to this structure. If you had direct access to the code underneath, you'd be responsible for checking information. But then that means that you would never check something that you didn't need to, right? So if you were a perfect programmer, doing everything in C or assembler would be faster. And if I had 3 wheels, I'd be a tricycle, right? Some of this enforced structure is there for a reason. And I will say that a lot of this slowdown has been mitigated a lot with modern compilers and interpreters. It's still there. There's no way around it. But it used to be literally 100 times worse. So with all that said, now we can start talking about how we define objects, both generally and in Python.